Stephanie said, I'm Claire, and I'm here from Tamer, visiting from Cambridge, Massachusetts. And yeah, today I know my talk title is a little mysterious, but I'll talk about what authors, neurons, and enterprise suppliers have in common. So yeah, at Tamer, I'm a field engineer, and I've been working for a while now on the problem of authordisambiguation. And I know that all of these things, Tamer, authordisambiguation probably mean very little to you guys. So I'll start off with a little bit of background on what Tamer is. So Tamer, I've been with Tamer since kind of late 2014, but Tamer as a company emerged kind of out of secret alpha mode in kind of early 2013. And two of our co-founders are Andy Palmer, who's a serial entrepreneur in the Boston area, and Mike Stonebreaker, who's kind of a database pioneer who's really well known for inventing Postgres and Ingress, and was actually the Turing Award winner last year. So these guys have worked on a lot of companies together, the last one being Vertica that was acquired by HP in 2011. But the Tamer team was a lot bigger than just the two of these guys. It spanned a team that was at MIT, UC Berkeley, and University of Waterloo. So a lot of these guys had worked together before, and they'd kind of been observing some problems in the world of big data. There was a lot of talk about data being big, but the volume was just one aspect. You guys have probably heard about kind of the 3 V's of data before. So there's the volume, the velocity with which all of that data is changing, and the variety of data sources that exist. And these guys were really interested in focusing on the variety of sources and figuring out how to work with all of those sources at once. So you have spreadsheets, you have databases, and when it comes time to integrate all of those sources, that was something that was proving to be a big challenge. So that's kind of a big picture of what Tamer is working on. How are these guys talking about kind of solving this issue of variety and big data? Well, there is a lot of kind of promise of what data could hold that people were recognizing across a lot of different industries. Andy was working in pharmaceuticals, but also people in manufacturing and advertising, just in general, were realizing, oh, if we do stuff with our data, we can make all these insights that can both kind of minimize the losses that we're seeing, and then also like maximize the revenue that we can see, and in general, we can just be better informed about our company. So we should do stuff with our data. But the processes that existed to do this were very timely and manual. And so, yeah, as this little guy demonstrates, things were moving along very slowly in the world of data integration. And so Tamer specifically came along, one, to help people discover the data sources that existed across their enterprise. So people, there's just a lack of visibility into the sources that existed. If you're an analyst at a company, you go in, maybe you email a colleague, you say, hey, what data do you have about this thing I'm meant to be working on? Maybe they send you a few files, and that's kind of what you're working with. So the idea is kind of build out a catalog of all of the data sources such that you know everything that exists. Once you know the data sources that exist, those usually won't be in perfect form. So kind of do a bunch of cleaning and transforming of that data, do some profiling on it so you know what it contains. Then it comes time to kind of look at the data sources that may contain common information and go about integrating those such that you have kind of a full picture of these entities that you're interested in. And then once you've integrated things, oftentimes once you put a bunch of data sets together, then you have a record for the same thing many times. So then there's this problem of deduplication. So that's kind of what Tamer does, and the idea was to do this in the most automated way possible. So they were building machine learning software that was kind of driven by a human expert that understood the data very well, and that was the idea behind Tamer. So what am I up to at Tamer? I thought this kind of, we call what I do field engineering. Usually when I describe what it is to most people, they're like, oh, you're a sales engineer. I'm like, yes, that's basically what I do. But yeah, so my job is kind of twofold. One is to go out into the world and to kind of identify data integration issues that people are having and kind of help them realize that we can help them solve them. And then once we get into these places, use Tamer alongside a bunch of tools and kind of platforms. So we see a lot of customers using Hadoop, where they've kind of thrown all their data, and then they're like, okay, now what do I actually do with this data lake? Some people who want to do the integration very quickly, so they'll run on Spark. Some people who want to visualize, so they'll use Tableau. We see a lot of other things out in the field. The idea is kind of integrate Tamer with all of these existing solutions in the field. For the past year or so, I've been doing less searching in the field for things to work on and more kind of focusing on the world of IP and science data and integration of the data types within this kind of realm. So we had a customer that came to us, and they had a bunch of different data kind of types that they were interested in integrating. So there's patent data, trademark data, general people data, organization data, funding data, and then academic articles. And kind of the dream for these guys was to be able to ask questions like, who are the people who are listed as inventors on a patent? Do they belong to an organization? If so, who actually has rights to the patent? Are there institutions that funded the work that led to this patent? What are the trademarks on those organizations? And kind of to paint a full picture of the entities that they look isolated in these data types, but are actually very related to one another. So we started talking about how we could use Tamer to do that, and then we realized that even just within the academic article kind of data type, there were a lot of problems to be solved. So that's where author disambiguation comes into the picture. So what is author disambiguation? Well, I think Science Magazine summed it up really nicely last fall. People in my company were like, what is this thing you're working on? And then Science talked about it, and they're like, okay, it's like a real thing. Yeah, so they cited an article showing how the person or the group that kind of is most respected for curating academic articles commented that there are these 3 very common names that make other academics look like total slackers. Each has published 30,000 papers in just 10 years, making for an average of 9 papers a day. So that's generally the problem. People refer to themselves in a pretty ambiguous way, oftentimes on academic publications. So then if you throw all of the articles in the world into a database, and then you say, who are the people on these articles, things get a little dicey. So just to kind of make this concrete, if we look at Google Scholar, say I want to look up all of Mike Stonebreaker's papers. So I type in his name, and I see that there's this very relevant thing. I know he works on databases. This is good. But wouldn't it be cool if I could click on his name and then actually get to a profile of Mike and a real list of all of the publications that he's worked on? So this page is very old. I don't think Mike has updated it in a while. But he had a total of 26 articles listed on this page back in 2003. And Google found upwards of 7,000 results. And so though he's published since then, probably not that many articles. So the general idea is figure out how we can actually make these properly curated lists of publications that people have worked on. So in doing that in the data, there are kind of 2 big challenges with the way that names are represented. There's identification and disambiguation. So identification is identifying the complete set of potential ways to refer to somebody. So in this case, you guys can kind of read this, but someone could use their first initial, their middle initial, or not. They could use their name. There also are very rarely kind of issues with data quality, but people typically tend to spell their name correctly on a publication, so we don't see too much of that. There's also the disambiguation problem. So this is where you see the same representation of a name on 2 different papers, and you have to figure out that they're actually 2 distinct people. So how do we do this? Well, just kind of to show you guys how we get to the state that the data is in once we start working with it. So a group of authors will submit a manuscript, and they pick a journal to submit that to. So say they submit to Nature. Nature accepts it, and they publish it in their own format. And then there are a bunch of people that come along, and they say, OK, we want to aggregate all of the publications that exist. So there are a bunch of people that do this. There's Google Scholar, Web of Science, Scopus, and they all say, some of them have more articles, and they say, we have all the articles. And some say, we have fewer, but they're higher quality. But they all kind of do the same thing. But they have their own kind of ways of normalizing the format of the papers when they come from different journals. So then you end up with a bunch of articles in a standardized format. And you have to figure out how to mine those articles of information such that you can find the original people. OK, cool. Just time check. So what author-relevant signals exist in the article? So the data type that you actually have is an article. So if you just kind of do deduplication on this set of data, you'll find that everything is distinct usually, because there's only one instance of each article. So extract the signals that are relevant to the author and then do deduplication is kind of the process. So there are attributes that are kind of specific to the author. There are their name attributes. There are the people they publish with. Sometimes there's an email, but typically only an email for kind of the primary author to correspond with. And sometimes that linkage isn't clear depending upon who's aggregating. So sometimes like Google Scholar will drop links sometimes, that sort of thing. The institution that the author is affiliated with, again, sometimes you have that. There's a full list of institutions, so there might be Waterloo and MIT listed on a Tamer paper, and you don't know if Mike is affiliated with Waterloo or MIT. Sometimes you do. So there's some stylistic kind of analysis you can do if you know that a certain author wrote the abstract, which there are some methods out there for figuring that out. And then you can use address information. So these are kind of author-specific attributes. There are then article attributes, so you can look for the subject of the paper, who published it, keywords of the paper, the language it was published in. And then it turns out the best thing that we have are these signals that come from, besides the author-specific attributes, come from a citation graph. So here, I'll kind of show how the citation graph is really useful to us. So say we have two articles, one with M.R. Stonebreaker, one with Mike Stonebreaker on them. How do we know if this person is the same person? Well, if you look at the citing articles, I work with Mike, so I probably cite his papers a bunch when I'm writing stuff up. And so if you see that there is a common article that's citing the same paper, that's a really good signal for it being the same author. And similarly, with the papers that are referenced, people tend to only read a small subset of the literature. You don't have someone reading, we have 60 million articles that we're looking at. No one reads all of those. So people tend to kind of reference the same thing over and over again. So if you have articles in common in the reference list, that's also a very good signal. So we have all of our attributes. How do we actually do this using Tamer? Well, we start out by doing some binning. So we if you were to compare every author with every other author, that would take a long time and wouldn't be very efficient. So for example, you don't really want to do the comparison that is Andy Palmer the same person as M. Stonebreaker. That's not something you need a machine to tell you isn't true. Here you have an ambiguous case where it's actually interesting. So Tamer goes through and it does a bunch of tokenization and NLP to figure out kind of dense regions of the data where there are pairs that are of interest to look into. Then a human comes along and Tamer picks a stratified sample of that pair. So it says, okay, here are all the pairs that we've picked to be reviewed. Here's a subset of those pairs that are kind of representative of the rest of them. Now, kind of a human expert go through and label those as match or distinct. And then we'll train a classifier based on your labels, which understands which attributes matter based upon your labels, how to weight those attributes, et cetera. And so each pair, ultimately, that Tamer identifies may be a match is assigned a probability of being a match. So finally, you have a list of pairs with a probability of being a match, and then you have to cluster those together. And so that's the process. And we actually found this worked really well. I do a lot of work with Thomson Reuters on the Web of Science, and we've been working on this model with them for a long time. We finally tested it on a subset of the model of their data, so 3 million authorships, and we found that we discovered a cluster for more than double the authors they were able to find before, and with higher precision than they were finding before. So that was great news. I was very excited, and I was like, awesome, we're good to go. Now we just need to run the full data set, and we're good. But you guys might remember there was a slide earlier that said challenge 1 out of 2. So there were 2. And it turns out the clustering piece of all of this was actually really tough. And we're almost finished working on it now, but it was a big challenge to overcome. So if you think about it, you have a list of all of these pairs and a probability that each pair is a match. But then when you look at how these pairs are connected to one another, you start to see that it's a really big computational task to figure out how to actually cluster these pairs. So in this case, paper or author C and D and author D and E are highly probable of being the same person. Same with C and A and E and G. But A and G, Tamer is like, no, definitely not the same. So then what do you do? And then you apply that to pairs generated from 60 million authorships, and things get kind of challenging. So everyone at my company was like, well, let's just use Spark. Let's just throw all these jobs onto Spark, and it'll be great. And I was like, okay, we can use Spark. I haven't used Spark before, but I've heard it makes things fast. Great, we'll do that. So this is kind of how I feel about what we were trying to do, even with 50, we had 50 nodes on our Spark cluster, but it just wasn't something that was possible to do. The computational kind of requirements behind the clustering using the model and the approach that we were doing just wasn't something that we could do in this way. So then we were kind of almost back to square one, but we had this model that was working really well, and it was like, well, we don't want to scrap everything and start over, so what do we actually do? And in thinking about this, the big lesson was don't try to determine something in a probabilistic manner that you already know is true. So I was thinking about, we have all these pairs and we're trying to figure out how to cluster them. And there are a lot of pairs that adds kind of in that example I showed are very highly probable of being matches. Turns out they're not very highly probable of being matches. They are matches. You can go in and just using human expertise, you can assign some high precision rules. So you can say, okay, I know that if somebody's first name, middle initial, last name is the same, and they publish with the same people, and it's, they use all the same keywords, et cetera. There are certain rules that you can apply to say these are definitely the same person. And you don't need Tamer to go through and do all of its fancy machine learning in order to learn that. So what we did then is we decided to do a pre-clustering on all of this before we kind of started doing the machine learning. So apply those rules, and then you have a bunch of kind of pre-clusters and with many entities in them. And then there's this kind of non-trivial step of figuring out how to merge those records into a representative record of all of them. So you have to figure out how to represent the pre-cluster. And so some attributes such as the references need to be merged, so you might pick kind of the most frequent values in certain attributes or something else. But we spent a long time kind of thinking about how to do this merge. Then you apply machine learning, and everything works nicely, or is almost working nicely. And we're still using Spark, and I think we should have results out soon. So that's kind of a picture of the problem of author disambiguation. But it turns out we see this same challenge in many domains, both at Tamer and kind of out in the world in areas that we don't work on yet. So there's this problem of having a bunch of really messy real-world data and really interesting entities within that real-world data, and you have to figure out how to find those entities and then cluster them such that you have a full picture of what they are in the world. And so we see this. We do a bunch of work in supply chains. This is where enterprise suppliers comes into the picture. We work with one company that has so many kind of purchase systems, and people in different divisions of the company refer to suppliers that they purchase from using different names, so just like authors. Then when you want to analyze like all of your spend with one supplier, or maybe like Intel did recently, you want to look into whether your suppliers are being compliant with certain regulations and not using child labor, that sort of thing. That's really hard to do when you don't have a unified picture and a true cluster of all of the data that you have about that supplier. So that's one other example of where this kind of shows up in the real world. Another, I was actually in neuroscience prior to coming to Tamer, and as I was thinking about this, the work that I did before was kind of similar to trying to get to the result really quickly by running on Spark. We were trying to figure out how do you extract a chunk of the brain, and then you want to actually see the neurons that appear in that kind of extract. So we were coming up with a gamified method to help kind of reconstruct neurons from neural tissue. So here's kind of a nice picture of a couple of those neurons in isolation. And we figured out how to really rapidly accelerate this process, both using kind of crowdsourcing, and then also the machine learning algorithms that go along with the process have improved a lot since just like when I was working on it. But then if you move into, once you put all these together, this isn't even kind of a fully dense picture, but the idea is that there are tons and tons of neurons that you can reconstruct, but ultimately what we're interested in is kind of figuring out the various classes of neurons in the brain, how those connections between classes end up resulting in things like thinking and behavior. But now we're just kind of throwing algorithms and people at the problem, trying to figure out how to reconstruct neurons one at a time, and then we're going to have to do the same kind of clustering issue all over again. So kind of same issue, totally different space. So I'll wrap up with a couple of takeaways that have become important lessons to me through this process. So one, be thoughtful about the data that you collect and how you manage it. So right now, a lot of authors will kind of put an identifier in there. Thomson Reuters in particular is working on kind of having an author identifier that is unique to an author and that they submit every time they submit a paper. So that's something that's emerging, and it's something like you might consider if you're collecting a bunch of data, try to have unique identifiers at the beginning, for example. The next one, a big one, apply human expertise before you do kind of all of this fancy machine learning and all these statistics on data. Really kind of think about how you want to solve the problem and then figure out how you can use machine learning as a tool. And finally, even though you can, don't just throw resources at a problem. We have a lot of access to all these cloud instances these days, and there's kind of a notion just, if you want a job to run fast, just use more nodes. And one, that doesn't always work, and two, the carbon footprint of doing that is a big one. I was just looking at how much energy we were using on this problem alone, and it's a little astounding. And it's an interesting space, but everyone's doing all this stuff. So just some thoughts that I have kind of pondered on as I've been doing this work. So that's everything I have. Thank you guys so much for coming on a Saturday. I'll be around after if there are questions. Great.
Thank you very much. Just a few announcements.